Alright, so let's go ahead and continue where we left off. Before we do so, someone give me a reminder, when is our first test of the semester going to be? Thursday. So yeah, this Thursday, immediately after this class, I will be posting a study guide onto Blackboard, so you get some extra practice and everything like that. Probably sometime on Wednesday, I plan to be posting the solution to those things in the study guide as well. So I highly recommend that you go through the study guide. Generally, the rule of thumb is if you can do that study guide relatively successfully without having to go back to your notes for every single problem, then for the most part, you should be fine on the exam. So, in other words, I'm not trying to do any special tricks or anything like that. Sure, I might change up numbers or change or something like that, or change patterns, but concept-wise, everything on that study guide should match generally concept-wise to what you might see on the exam. So the study guide might have a couple of extra concepts that are not covered on the exam, but the exam will only cover stuff from the study guide. And again, that just means if it's not in the study guide, you can for the most part safely assume that it's not on the exam. Alright, so let's go ahead and continue into our lecture. What was the thing that we talked about last time? What did we introduce? What was the big rule? Yeah, we had the binomial theorem, and in particular, we used it to prove the power rule. So just a recap of what we did before, we talked about the power rule. Which stated that if I take the derivative of x to the n power, what's the derivative of x to the n power? What did the power rule say it was? Yes. The derivative of x to the n power is n times x to n minus 1. Or, as you'll commonly hear me say, we'll bring down the exponent power and then reduce the power by 1. So we looked at this and then we said that this should apply for any real number n. This means that you can deal with it whenever the exponent is a positive whole number. It can also work whenever we have a fraction as our power. And it works also whenever we have a negative power. Or even if we have an irrational power. So I mentioned last time that if there's nothing else you pick up from Cal 1, at the bare minimum, you should remember the power rule. Again, bring down the exponent power, multiply it to the front, and reduce the power by 1. So, just so that we can make sure everyone's on the same page, let's do a quick example. I'm going to give 3 examples, and we're going to see how do I solve it. So, let's find f. Let's start off with a nice quick warm-up. Let's say I do 3x to the fifth power minus 2/3 x. Probably going to have 3 parts, but I'll write them up as we go through it. So we have 3x to the fifth minus 2/3 x to the 1/2 power. And I want the derivative f prime. Alright, so can someone go ahead and actually just tell me what is going to be the derivative of this function? What should I write down? There's 15 x to the 4th power. Anything else? 1/3 x negative 1/2. I would look at this and I would probably agree, yes, this is going to be the derivative. Let's just talk very quickly about how I got that. First thing is that I'm applying the power rule here because our function is x to a power. That's a good sign telling me yes, I can go ahead and apply the power rule. So for this first one, I took the power and multiplied it to the front. So 5 times 3, I got 15. And then I subtracted 1 from the power, which is how I have a power of 4. And I essentially do the same thing here on the other side. I bring down the 1 half. Negative 2/3 times 1 half, we get negative 1/3. And then 1 half minus 1, we get negative 1 half. So once again, I just have my derivative via applying the power rule. Again, I want to note here that there's not really much work to be shown here. It looks like it's just a one-line problem, which does tell me I need to be careful because it's very easy to actually make a multiplication mistake going through this. So this was a little bit of our warm-up. Let's go on to part B now. What if I have something like this? Let's say I have f of x is equal to, let's do 7 over x to the 9th power plus x to the power of pi. And once again, I just want the derivative f prime. So before I even attempt to find the derivative, looking at this, am I allowed to apply the power rule immediately? No, because my power rule said I can only apply it whenever it's just maybe a coefficient x to the power of n. It said nothing about what happens whenever I'm dividing by x or anything like that. So what might I want to do before I try to take the derivative? Yes. So the 7 is still there. Remember, we have an algebra trick where I'm allowed to bring this x to the 9th and bring it to my numerator by making x to the negative 9th power. So this is again using the fact that x to the negative 1 is the same thing as 1 over x. We're using that same property. And I still have x to the power of pi here. In fact, let me just rewrite this pi a little bit nicer so it's clear. Alright, so looking at this, does it look like I now just have a combination of x to the n powers? For sure. This tells me let's go ahead and apply the power rule. So, what's the derivative of 7x to the negative 9th power? Yes. So we just brought down to negative 9. 7 times negative 9, we get negative 63. X to the negative 9 minus 1, we get negative 10. Well, that's good. We got the derivative of 7x to the negative 9. What about the derivative of x to the power of pi? Yes. So I agree. We brought down the power of pi to the front, and then we subtract 1 from the power. So we have x to the power of pi minus 1. Because pi is just a number. Granted, it's an irrational number. It's not really clean for us. But it's still a real number. And there's not much left for me to do here because, again, pi is irrational. In fact, it's already simplified if I just leave it as pi minus 1. So great. We have that. All right. Any questions about parts A and B before I move on to C? And we'll do C, and then I'll have another example with 2 parts. All right. So part C. What if I have f of x is equal to Let's keep it simple. Keep it as 20 over the fifth root of x to the sixth power. So we'll leave it at that. So immediately, what's the issue? Why can't I apply power rule immediately? Yeah, a couple of reasons I would take. For example, it's not just number x to a power. Here, my x on the bottom, I may have some issues. How might I want to rewrite it? Well, the 20 is staying there. Nothing's changing there. Yeah, so just for the sake of notes, usually I would do this in one step, but just so that we're all on the same page. First thing is the fifth root of x to the sixth. Yeah, this is the same thing as x to the, well, in this case, 6 over 5. And then I can just apply my negative rule. It's the same thing as 20x to negative 6. Remember that we can always turn a radical into a fraction exponent. Kind of like the square root of x, that's the same thing as x to the 1/2 power. Same principle here. Power on the inside goes on top. The type of radical, in this case a fifth root, that becomes my denominator. So now it definitely looks like number x to a power. Let's go ahead and apply my power rule. So f prime of x, bring down the power of negative 6 over 5. What's negative 6 over 5 times 20? Yes, I agree. Negative 24. Quick way we could have done that. 20 divided by 5, we get 4. 4 times negative 6, negative 24. And then what should I write next? X to what power? Yes. So all we did was bring down the power and then subtract 1. Negative 6 over 5 minus 1. That's the same thing as negative 6 over 5 minus 5 over 5. So negative 6 minus 5, we get negative 11 over 5. And then once again, we're done. Again, it looks like now we just have these one-step problems. Yeah, so right here, just writing it down. Whenever we multiplied it out. So here, the way that might be easier, it says doing 20 times 6 divided by 5. You can also do 20 divided by 5, so 4, and then 4 times negative 6, negative 24. Because we know that essentially our idea of multiplication and division, the order doesn't really matter that much. I didn't have to say 20 times 6 and then divided by 5. I could have said 20 divided by 5 and then 6. Well, negative 6 in this case. But yeah, we have our derivative. So again, a lot of practice, just making sure, first off, can we multiply this correctly? And do I remember to reduce the power by 1? A couple of the most common mistakes that I see. I commonly see mistakes with fractions, as you can imagine. Other mistakes is whenever we see a negative exponent, I see a lot of people accidentally add 1 instead of subtract 1. Remember, for the power rule for differentiation, we're always subtracting 1 from the power. All right, so I have a couple of examples here with the power rule. Obviously, much faster than whenever we had the limit definition and had to go through that way. Now we have this nice method to essentially do each of these really quickly. So the power rule is really great, and it continues to be really useful through Cal 1, Cal 2, Cal 3, differential equations, and anything that involves any level of derivative or rate of change or slope in the future. What are some limitations of the power rule? Because this rule is really strong, but what are some limitations of it? What are something that I can't take a derivative of using the power rule? What was that? I would say irrational numbers is still fine because we had the x to the pi power, and pi is irrational. Yeah, for example, if I had variables on the top and the bottom, let's say I had like x plus 1 divided by x squared plus 3, I can't really apply a power rule because I can't really simplify that down into x to a power. So whenever I have some complicated division, I might have a problem. Or even whenever I have more complicated multiplication. That is, for example, next example, find the derivative. Yeah, part A and B. Notice here that I didn't say find f prime of x because I'm going to change it up slightly with my uh, variables. Alright, so let's say I have y is equal to, let's do x. We'll start off nice and quick with x plus 1. If you've taken calculus before, you might know that there is another rule in the future that we might use. But for now, let's stick with our power rule. So why am I not allowed to use power rule immediately here? It definitely just has x's and looks like regular powers, but why can I not immediately apply power rule? There's coefficients. In particular, for my power rule, it was very strictly whenever I just have x to a power. This one is x plus 1 to a power. So again, that power rule is used whenever I strictly have an x to a power, not an x plus 1 to a power or anything like that. So I can't apply power rule immediately here. So how do I get around that such that I am allowed to apply power rule specifically? Yeah, I can look at this and if I wanted to, I can multiply this out. Remember what x plus 1 squared is? That's just x plus 1 times x plus 1. That is, I can multiply this out if I really wanted to, and we will. So multiplying this out, quick algebra recap. In this case, we have a binomial times a binomial. If you really want to use the terminology, we can FOIL it out. First times first, x times x, yeah, x squared. Oh, for outside, x times positive 1, get plus x. Inside, 1 times x, again, I get plus x. And then last, 1 times 1, yeah. So I have x squared plus 2x plus 1. This is still my original function. So, am I allowed to use power rule now? Yes, for sure. I definitely have a combination of just x to a power each time. So, first off, what notation do I use for the derivative of y? What are my options? Because I don't write f prime yet, so there's no f here. Yeah, we can write y prime. Or remember the other option is you can use dy. Again, these mean the same thing, just depending on the book. If any of y'all are taking differential equations, you will definitely see a lot of dy dx in the future. You don't have to write both of them. I'm just writing both of them to say it's either option. They're both a standard notation. So what's the derivative of the right side? X squared plus 2x plus 1. What should I write? 2x plus 2. Yeah, and then we have plus 0, but I'm not going to bother writing plus 0 because plus 0 doesn't change anything. So I claim I have my derivative. I want to go on a slight tangent before I go on to part B. I want to talk really quick about this notation dy dx. Again, this means the derivative of y in respect to x. This tells me I had a function y, it was in terms of x. So this means that I could easily change up my letters if we were in a different scenario. For example, if you're working in physics, you have functions of time. So maybe you would have, in physics, you might use dy dt, the derivative of the function when we're talking about the variable time, stuff like that. So I just wanted to make a small note about that. If you ever see a different letter, make sure that you change it. So with that, let's go ahead and do a part B. Yes. Yes. Here we can pull it out and then we can take the derivative. Plus 2. Oh, so right here. Would you agree that here we have a power of x to the 1? So I can still use the power rule, bring it down to 2 times 1, we have 2. Reduce the power by 1, we have technically 2x to the 0. And then x to the 0, that's just 1. So 2 times 1, that's where we're getting the 2. And right here, the derivative of 1, that's 0. Yes. What part do you want to talk about specifically? So which part exactly? The 2x part or whenever we start mentioning 1? Yeah, so the derivative of 1 is 0. Someone tell me why that's the case. Why the derivative? There's a couple of explanations why. You can either do it from an interpretation about what the derivative means, or you can use the power rule still. So here's the two ways we explain it. First way through the power rule. And this original problem, would you agree that it's the same thing as 1x to 0? Because that's still just times 1, right? So what happens when I apply the power rule? Bring down to 0, 0 times 1, you get 0, then 0 times whatever this x is, it doesn't matter, 0 times whatever, you get 0. So in this case, we have 0x to the negative 1, for example, but that's still 0. That's one way you can explain it. The other way is think about the function 1. What does the graph of 1 look like if you were to graph it? It's just going to be a flat line, right? What's the slope of a flat line? 0. And we said the derivative and the slope are almost interchangeable. In fact, I said that the derivative is essentially a generalization of the slope. So that's the interpretive way you could have said it. If I look at function 1, it's a flat line. What's the slope of a flat line? 0. So that's also matching up with 0 here. Any other questions about this topic? Did that clear it up a little bit? Cool. All right, so let's work with a part B. What if I get y is equal to, um, let's do 5 squared 2x all over. I meant to use a different letter, but we'll use y. All right, so first off, I definitely cannot use power rule here because, again, it's just supposed to be the sum and difference of x to a power. In other words, I should only be able to apply power rule, strictly speaking, when I'm dealing with a polynomial or polynomial-like function. Again, coefficient x to a power, and then maybe adding a bunch of them. I cannot apply it here because the clear thing is I'm dividing by an x. I have x on the top and the bottom. But this isn't much of an issue here. Plus 2x over 3x. So I'm allowed to split up the fraction. It's a little bit opposite than what we're used to. We're used to using common denominator, making one fraction. but there's nothing stopping us from going the reverse. Again, I have not done any derivative work yet. I've just done some algebra to clean this up. Yes, exactly. This benefits us because now I can just go ahead and do some nice simplification. 5x squared over 3x, I get 5/3 x. Or you put 5x over 3, it's the same thing. Usually I just like writing the x on the side so that I can see very clearly I have a coefficient and then an x. Plus, what should I write next here? Yeah, 2 over 3. Alright, so I claim now that I am prepared to go ahead and apply the power rule. What is going to be my derivative? What should I write completely starting from the beginning? So we have 5 over 3. Should I write anything else for my final answer? Should I just write 5 over 3 alone? Yeah, let's use dy dx or y prime, whichever is your preference. We just want to make sure that we are saying this is the derivative. We're just not writing 5/3 out there randomly. Seems like a little tedious thing, but whenever we start working with more derivatives, we have to make sure that we know this derivative is this derivative is this one. This will be especially important whenever we start doing applications. We want to make sure that we have the right derivative labeled. So again, you can use dy dx, or if you want, you could have easily written this. That's still the same thing. Either one, perfectly fine. They both mean derivative of y. The reason why this one is used a lot more in GE because you can imagine if we're working with more letters, we want to know what the function was originally. So we know this original function had x in it, for example. But y prime is equally common, especially whenever you don't want to be writing dy dx over again. 2, 3. Same thing as the one. 2/3 if I wanted to. The same thing as 2/3 x to 0 because there's an understood one x to 0 there. This does give us a slight note to make. What is the derivative of a constant? 0. So if I'm ever taking the derivative of something that's just a plain number, there's no x's, the derivative is always 0. So you can also use that idea. 2/3, that's a constant, it has no x's, that are really important. The derivative is 0. And also, it's always good to note, but usually I don't bother writing plus 0 as an extra step because plus 0 is not going to change anything. All right, so any questions so far about the topics, about any of these examples? So I'm going to give you a couple of examples where power rule will not work. You do not have to write these, but it's sometimes good to recognize when the just straight power rule is not really useful. So let's say it has this. There's no way for me to immediately apply a power rule here or even do algebraic manipulation. Last time we were able to do it because before it was a single monomial x. Yeah. Well, we could try multiplying by the conjugate, but it's not really going to get rid of the x on the bottom. Because you know how before, whenever we split it up, it got rid of the x on the bottom. The conjugate might help simplifying somewhere else, though. So this is something where the power rule alone is not useful for us. We would have to use more techniques that we'll learn in the future for that. Here's another thing where I'm going to give you an example where power rule, technically you could use it, but you probably would not want to use power rule in its current state. X plus 3. Why would I not want to use power rule there? So the reason before we were able, so technically here we can use power rule, but I would have to multiply it all out. You can imagine that's not going to be a good experience. Whenever we had square, we said, all right, that's not too bad. That's not that much work. I can multiply that out fairly quickly. But if I put this as 296 power, and I said find a derivative right now, the only real way would be, based on what we know, is if I multiply this all out 296 times multiplication. But obviously, we're not going to do that because that's tedious. That's just busy work. So these are some examples of problems where power rule is not going to be sufficient for us, or it's not very convenient. This is why in the future we will be covering things like just some buzzwords. Again, if you've taken calculus before, you'll recognize some of these. Product rule, quotient rule, chain rule, um, trig function, derivative of inverse trig, derivative of exponential function, derivative of log function. Um, we're not going to cover hyperbolic functions, but that is a different type of function. It's one of those ones where you might have seen it in a book before, something like that. But we're not going to cover those because we don't really talk much about hyperbolic functions. Then we're going to talk about equations that are not functions. For example, how do I take the derivative if I'm working with the equation of a circle? A circle is not a function, but I can still find the derivative somehow. Things like that. So the last thing I'm going to cover for today is I'm actually going to take one of those and show y'all the derivative. So I'm going to show you the next, what's considered the next easiest derivative besides power rule. That is the exponential, well, let me be more specific, the natural exponential function. Natural exponential function. That is the famous e to the x. So the question is, what is the derivative of e to the x? And why am I claiming that this one is actually going to be a fairly straightforward one? First off, I want to point out, this is not power rule. Why is this not power rule at all? Yeah, before, power rule said x to a number power. Here we have a number to the power of x. So the derivative of e to the x is e to the x. Again, I want to point out here, I'm not saying the derivative of like negative x, the derivative of x, e to the x squared, just plain e to the x. This is actually the only non-trivial function where the derivative is itself. So if I ever ask what's the derivative of e to the x, you should tell me e to the x. We are not, right at this point, we're unable to do this. We don't know how to get the derivative of e to the x squared. Or nor do we know how to do something like e to the negative x per se. So I'm going to emphasize here for right now, we're only dealing with e to a positive x. So we have my natural exponential function derivative. Does anyone actually know more or less what the value of e is? If you put that into your calculator, what is the number e roughly? So e to the x, if I remember correctly, should be, I believe, roughly like 2.71, something like that. It's called Euler's constant. This right here is called Euler's constant. The reason that we actually talk about this, I'm going to go on a slight tangent here, is that E is called the natural base, If you have ever heard of the natural log, is related to that. The reason why it's called natural is because it actually does. This number actually shows up a lot in nature. You look a little bit into Fibonacci sequence, golden ratio, all that fancy stuff. The number, if you count the number of diamonds on a pineapple, it's related to this number here. So there's some ratio things that go on that's really interesting, but again, we're not going to go super deep into it. So let's finish this up with just one quick example. Example. Find the derivative. And let's change it up by saying, let's say if I have a function y is equal to 7/3 e to the t power plus e to the negative second. I claim that we should be able to do this fairly quickly. First off, what is the notation for my derivative? What should I write exactly? Y prime is sufficient. What's the other way I might write it? dy, and in this case, we have a function of t. In this case, it would be technically dy dt. That's what I mean by just change up the lettering a little bit. That's the only difference that really changes. Instead of dy dx, it would be dy dt, for example, because we're a function of t. We depend on the variable t. All right, so the derivative of 7/3 e to the t power. What is that derivative? 7/3, because that's a coefficient. Derivative of e to the t, to the t. That part's good. One thing I want to note also is notice here that the coefficients, they kind of go along for the entire derivative process. Maybe they get multiplied by something, but usually they're still there somewhere. What about the derivative of e to the negative second power? Negative 2e to the negative third. Let me write that down. 2e to the negative third. Do we agree with this? I'm going to make the claim that this not be there. Why is that the case? Why is it not negative 2e to negative e to the negative third? Yeah, why am I not using power rule for that? Yeah, because e is a number to the negative second power. For example, if I wrote this on the side, and I said get the derivative of that, that's the same thing as 1/9. You would say the derivative of 1/9, that's a number, that derivative is 0. Here, e, again, I want to emphasize e is by itself is just a number. There's no other variables on this portion. You can put this into your calculator and it's going to give you a constant. E to the negative second is going to be 1 over e squared. So the derivative of e to the negative second power is 0 because it's just a constant. In the end, it's a number. There were no t's in there. So that means I have my answer. And usually this is the one that I have a lot of students request that they add on or a question where they say, give me something that has e to the t, either like the derivative is itself. All right, so any questions about the derivative of this exponential function? As you probably noticed, I didn't really do a lot of examples of this because there's only so many numbers that I can put in front of e to x. Oh, it's still interesting. All right, besides that, I believe that's all I have for y'all today. Starting tomorrow and Wednesday, I plan for that to be mainly review days for our exam on Thursday. So I will be posting that study guide. You get some access to old exams and everything like that. If you have any questions, please let me know. Remember, I do have office hours on, especially tomorrow from 2 to 5 p.m. in my office. My office is quite literally down the hallway. All right, I'll see y'all tomorrow.